The universe is not a calm or comfortable place. It is not designed for life, and it does not exist to support anything fragile or familiar. From the smallest particles drifting between stars to the largest cosmic structures spanning billions of light years, everything is shaped by forces that operate on scales far beyond human experience. Temperature, pressure, gravity, and radiation reach extremes that cannot exist naturally on Earth. What we consider survivable here is only a tiny, narrow range in a much larger and far more violent cosmic spectrum. Beyond that range lies a universe filled with conditions so extreme that even imagination struggles to fully comprehend them. To understand these extremes, it is important to begin with perspective. On Earth, life exists in a relatively stable environment. Temperatures fluctuate within a range that allows water to remain liquid. Atmosphere provides protection from harmful radiation. Gravity holds everything in place without crushing it. These conditions are not universal. In fact, they are rare. Most of the universe is either too hot, too cold, too dense, or too empty for life as we know it to survive. Earth is not the standard, it is the exception. As we expand our view outward, the first thing that becomes clear is that temperature is not evenly distributed across the universe. There are places so cold that atoms barely move, and others so hot that matter itself cannot maintain structure. These extremes are not theoretical. They exist in real environments scattered across space, from the vast emptiness between galaxies to the violent cores of dying stars. The difference between these environments and Earth is not just a matter of degree. It is a difference in physical behavior, where the rules of nature begin to push matter toward its limits. In the coldest regions of the universe, temperature approaches a theoretical minimum known as absolute zero. At this point, atomic motion nearly stops. While it is impossible to reach absolute zero completely, certain regions of space come incredibly close. Deep interstellar clouds, far from any star, can reach temperatures only a few degrees above this limit. In these regions, gas and dust drift slowly, barely interacting, forming structures that evolve over millions of years. These clouds are often the birthplaces of stars, but in their cold state, they are almost entirely silent and inactive. Even colder conditions exist in the vast emptiness between galaxies. These regions are not completely empty, but they are so thinly populated with matter that they are effectively frozen in time. Without nearby energy sources, particles lose energy, and movement becomes minimal. In some parts of space, temperatures can drop so low that they challenge our understanding of thermodynamics. These areas represent some of the most extreme cold environments in existence, where heat is almost entirely absent. Coldness in the universe is not only about temperature, it is also about the absence of interaction. Without energy input, systems slow down, processes halt, and change becomes rare. In these environments, time itself feels different on a physical level because evolution of matter occurs so slowly. It is a universe in pause, waiting for something to disturb its stillness. In contrast, the hottest regions of the universe are defined by unimaginable energy and motion. Stars are the most familiar example. Our Sun, for instance, is already hot enough to sustain nuclear fusion in its core, reaching temperatures of millions of degrees. But even the Sun is relatively moderate compared to the most extreme stars known. Some stars burn at temperatures so high that they exist only briefly before collapsing or exploding. Massive stars consume their fuel rapidly, generating intense heat in their cores. This heat drives nuclear reactions that produce heavier and heavier elements until the star can no longer sustain itself. At this point, the balance between gravity and internal pressure breaks down, leading to catastrophic collapse or explosion. These processes release energy on a scale that dwarfs anything produced by human technology or natural planetary activity. When such stars reach the end of their life cycles, they can explode in events known as supernovae. These explosions are among the most powerful in the universe. In a matter of seconds, a single star can release more energy than an entire galaxy produces in the same time period. The temperatures generated during these events are so extreme that they allow the creation of heavy elements like gold, uranium, and platinum. These elements are then scattered across space, eventually becoming part of new stars, planets, and even life itself. The aftermath of these explosions creates regions of extreme danger. Shock waves travel through space, heating surrounding gas to millions of degrees. Radiation floods the area, making it hostile to any nearby planets or systems. These supernova zones are not just destructive, they are transformative. They reshape galaxies, redistribute matter, and influence the formation of new star systems. In this way, destruction becomes a necessary part of creation in the cosmic cycle. Beyond stars, even more extreme conditions exist near compact objects like neutron stars and black holes. Neutron stars are the collapsed cores of massive stars that have undergone supernova explosions. Despite being only a few kilometers in diameter, they contain more mass than the Sun. Their density is so extreme that a single teaspoon of neutron star material would weigh billions of tons on Earth. The surface conditions of these objects involve immense pressure and intense heat, creating environments where normal atomic structures cannot exist. In some cases, neutron stars possess extremely strong magnetic fields, becoming what are known as magnetars. These objects generate magnetic forces billions of times stronger than anything found on Earth. Such fields can distort atomic structures and affect space itself in their vicinity. If a magnetar were placed at the distance of the Moon from Earth, it could potentially disrupt electronic systems across our entire planet. These are not gentle objects. They are cosmic engines of destruction and energy. Black holes represent another extreme entirely. They are regions where gravity becomes so strong that nothing, not even light, can escape. At the center of a black hole lies a point of infinite density, where known physics breaks down. Surrounding this point is the event horizon, a boundary beyond which all paths lead inward. Time and space behave differently near these objects. As matter approaches a black hole, it is stretched, compressed, and heated to extreme levels before being absorbed. The regions around black holes are among the most violent in the universe. Accretion disks of gas and dust swirl at incredible speeds, heating up due to friction and gravitational forces. These disks can emit enormous amounts of radiation, sometimes outshining entire galaxies. While the black hole itself cannot be seen directly, its effects on surrounding matter make it one of the most powerful forces in the cosmos. Not all extreme environments are distant or theoretical. Some exist within our own cosmic neighborhood. Planetary bodies within our solar system also experience conditions far beyond human tolerance. Venus, for example, has a surface temperature hot enough to melt lead due to its dense atmosphere and runaway greenhouse effect. Jupiter's moon Io is covered in constant volcanic activity, driven by tidal forces that stretch and compress its interior. These worlds demonstrate that extreme conditions are not limited to deep space, but can exist anywhere under the right circumstances. Radiation is another defining feature of dangerous cosmic environments. High-energy particles travel through space at nearly the speed of light, originating from stars, supernovae, and active galactic centers. In certain regions, radiation levels are so high that they would be instantly lethal to unprotected life. This includes areas near pulsars, quasars, and galactic cores, where energy output reaches levels that far exceed anything produced by normal stellar processes. Despite these extremes, the universe is not entirely hostile. It contains regions of stability where matter can form, stars can exist, and planets can develop. These stable regions are rare compared to the vastness of space, but they are essential for the existence of life. The balance between extreme and stable environments is what shapes the structure of the cosmos. Understanding these extremes is not just an academic exercise. It provides insight into the fundamental laws of physics. By studying the coldest, hottest, and most dangerous places in the universe, scientists learn how matter behaves under conditions that cannot be replicated on Earth. These studies help refine our understanding of energy, gravity, and the evolution of cosmic structures. The universe is a place of contrasts. It contains both stillness and violence, creation and destruction, order and chaos. These extremes are not separate from each other. They are interconnected parts of a single system. Stars are born in cold clouds. They die in explosive heat. Black holes form from collapsed stars and influence entire galaxies. Every extreme environment plays a role in shaping the cosmos. As we look deeper into space, we begin to realize that what we consider extreme is only relative to our experience. The universe does not operate within human comfort zones. It operates according to laws that allow for a vast range of conditions, many of which are far beyond anything found on Earth. In this sense, Earth is not the center of normality. It is a small pocket of balance within a much larger and more extreme reality. The journey into understanding the universe begins with recognizing this fact. We are not observing a calm and predictable cosmos. We are observing a dynamic system where extremes define structure and evolution. From the coldest voids to the hottest stars, from silent emptiness to violent explosions, the universe is constantly pushing the boundaries of what is possible. This is only the beginning of that journey. Cold is often thought of as the absence of heat, but in the universe it is far more than that. It is a condition that shapes matter, slows time on a physical level, and creates environments where change becomes almost impossible. While heat is associated with energy, movement, and activity, cold represents stillness, preservation, and silence. In the deepest regions of space, cold is not just a temperature measurement, it is a defining force that determines how galaxies form, how stars are born, and how matter evolves over billions of years. To understand the coldest parts of the universe, we must first understand how heat is distributed in space. Heat in the universe comes primarily from stars. These massive nuclear furnaces emit energy in all directions, warming surrounding space and influencing nearby matter. However, space itself is mostly empty. Between stars lies vast regions of near vacuum where there is almost nothing to absorb or retain heat. In these areas, temperature drops dramatically because there are so few particles to carry energy. The coldest known environments are found in deep interstellar and intergalactic space. These regions are so far removed from any star or galaxy that they receive almost no external energy. Without radiation, without collisions, and without nearby sources of heat, matter drifts in an almost frozen state. Temperatures in these regions can approach only a few degrees above absolute zero, the lowest possible temperature in the universe. At this point, atomic motion becomes extremely slow, and physical processes nearly come to a halt. One of the most fascinating examples of extreme cold exists in dark molecular clouds. These vast structures are composed of gas and dust spread across light years of space. Despite their size, they are incredibly cold, often only a few tens of degrees above absolute zero. Inside these clouds, gravity slowly pulls material together. Over millions of years, this process can lead to the formation of new stars. In this sense, cold is not just a state of inactivity, but also a necessary condition for creation. Without these cold regions, stars like our Sun would not exist. Inside these clouds, chemistry behaves in unusual ways. At such low temperatures, atoms and molecules move slowly enough to combine and form complex structures. Simple molecules like hydrogen and carbon monoxide are common, but more complex organic compounds can also form. These environments are considered important in the study of the origins of life, because they demonstrate that the building blocks of life can form in extremely cold conditions long before any planet exists. Beyond these clouds lies even colder territory. The space between galaxies is one of the most extreme environments in the known universe. Here, matter is incredibly sparse. A single cubic meter of space may contain only a few atoms. With so little interaction between particles, there is almost no transfer of energy. As a result, temperatures in these regions can drop extremely close to absolute zero. This is not a cold that can be felt or experienced in any human sense. It is a fundamental physical condition where motion itself becomes minimal. Even in these regions, however, cold is not entirely uniform. Cosmic background radiation, the leftover energy from the early universe, still permeates all of space. This faint radiation provides a minimal temperature baseline, preventing the universe from reaching absolute zero. It is a reminder that even the coldest places are still connected to the history of the cosmos. In these extreme cold environments, time itself behaves differently in subtle ways. While time does not stop, physical processes slow dramatically. Chemical reactions become rare, and changes in structure take immense periods to occur. This creates a universe that is in a state of near suspension. Galaxies drift slowly through space, and large-scale structures evolve over billions of years with very little internal change. Cold, in this sense, preserves the universe in a slow-moving state. Closer to Earth, cold also plays a critical role in shaping planetary systems. Many of the most interesting cold environments in our solar system exist on distant moons and dwarf planets. These worlds are far from the Sun and receive very little warmth. Their surfaces are often covered in ice, frozen gases, and solid compounds that would behave very differently on Earth. One example is the distant dwarf planet Pluto. Once considered the ninth planet, Pluto exists in a region of the solar system where sunlight is extremely weak. Its surface temperatures are so low that nitrogen, methane, and carbon monoxide can exist as solid ice. Despite this, Pluto is not a completely static world. Geological activity, possibly driven by internal heat, creates regions of change and movement. Even in extreme cold, complexity can still exist. Farther out, the moons of the outer planets reveal even more extreme cold environments. Many of these moons are covered in thick layers of ice, sometimes spanning kilometers in depth. Beneath these icy surfaces, however, there may be hidden oceans of liquid water. These subsurface oceans are kept in liquid form not by heat from the sun, but by internal forces such as tidal heating. This creates environments where liquid water exists in some of the coldest regions of the solar system, challenging traditional assumptions about habitability. The existence of these hidden oceans raises important questions about life in cold environments. On Earth, life is often associated with warmth and energy. However, in the universe, life may not require warm conditions in the way we expect. Instead, it may adapt to extreme cold, using chemical energy sources rather than sunlight. This possibility expands the definition of habitable environments far beyond traditional Earth-like conditions. In deep space, cold also affects the behavior of light and radiation. In extremely cold regions, electromagnetic radiation becomes weak and diffuse. Without nearby sources of energy, light travels long distances without significant interaction. This contributes to the dark and silent nature of interstellar space. It is not darkness caused by absence alone, but by the overwhelming scale of emptiness. Another important aspect of cosmic cold is its relationship with structure formation. In the early universe, after the Big Bang, matter was hot and dense. As the universe expanded, it began to cool. This cooling process allowed matter to clump together under the force of gravity. Without this drop in temperature, stars and galaxies would not have formed. Cold, therefore, is not just a condition of the present universe, but a necessary part of its history. As matter cooled, hydrogen atoms formed, eventually leading to the creation of the first stars. These stars then began producing heavier elements through nuclear fusion. Over time, cycles of star formation and destruction enriched the universe with complexity. All of this was made possible by the gradual cooling of space. In this sense, cold is deeply connected to creation itself. In modern astrophysics, scientists study cold regions using specialized instruments that detect faint signals across space. These observations help map the structure of interstellar clouds, measure cosmic background radiation, and understand the distribution of matter in the universe. By studying cold, scientists are effectively looking back in time, observing conditions that resemble the early universe. Cold environments also provide insight into fundamental physics. At extremely low temperatures, quantum effects become more visible. Particles begin to behave in ways that are not seen at higher temperatures. This allows scientists to test theories about matter, energy, and the nature of reality itself. Some experiments even recreate near-cosmic cold conditions in laboratories to study these effects in controlled environments. Despite its importance, cold is often overlooked compared to more dramatic cosmic phenomena like black holes or supernovae. However, without cold, none of these events would exist in their current form. Cold provides the background against which all cosmic activity occurs. It is the silent stage on which the universe performs its most dramatic events. There is also a philosophical aspect to cosmic cold. It represents stillness in contrast to motion, emptiness in contrast to structure, and silence in contrast to energy. It reminds us that the universe is not always active or violent. Much of it exists in a state of quiet balance, slowly evolving over immense timescales. This perspective changes how we understand our place in the cosmos. Even on Earth, cold plays a role in shaping life and environment. Ice ages have transformed the planet multiple times, altering ecosystems and influencing evolution. In this way, cold is not just a cosmic phenomenon, but also a planetary force that affects life directly. It shapes landscapes, controls climates, and influences biological development. In the broader universe, cold is not an exception, but a default state. Most of space is cold, and most matter exists in conditions far below those required for life. Warmth and energy are localized phenomena, concentrated around stars and energetic events. This makes life-bearing environments extremely rare and valuable. As we continue to explore the universe, understanding cold becomes increasingly important. It helps us understand where stars form, how galaxies evolve, and what conditions are necessary for life. It also challenges our assumptions about what environments can support complexity. Cold is not simply the absence of heat. It is a fundamental part of cosmic structure. The coldest regions of the universe are not empty or meaningless. They are active in their own way, shaping the flow of matter and energy over time. They preserve the history of the cosmos and provide the conditions necessary for future change. In their silence, they hold the potential for creation. As we move forward in exploring the universe, cold will remain one of its most important and least understood aspects. It is the foundation upon which much of cosmic structure is built. From the birth of stars to the evolution of galaxies, cold plays a hidden but essential role. In the next stages of our journey through the universe, we will move from these silent, frozen regions to places of intense heat and energy, where matter behaves in completely different ways. But even there, the influence of cold will remain in the background, shaping the balance of the cosmos. In the vast structure of the universe, not all cold regions are shaped by distance from stars or the expansion of space alone. There are places so isolated, so completely removed from any source of energy, that they exist in near total darkness. These regions are not simply cold in the ordinary sense. They are places where matter itself is stretched thin across unimaginable distances, where atoms rarely meet, and where the concept of temperature becomes almost meaningless. These are the coldest, starless regions of the cosmos, vast voids where the universe appears to hold its breath. To understand these regions, it is necessary to move beyond galaxies and even beyond the clusters that bind them. Galaxies are not evenly distributed in space. They form along massive filaments of matter, creating a cosmic web that stretches across the observable universe. Between these filaments lie enormous gaps known as cosmic voids. These voids are not completely empty, but they are so sparsely populated that they are among the most isolated environments in existence. In these regions, galaxies are few and far between, sometimes separated by tens or even hundreds of millions of light years. Inside these voids, conditions are extreme in a different way from the violent heat of stars or the crushing gravity of black holes. Here, the dominant feature is absence. There is almost no matter to interact, no radiation to absorb, and no significant energy flow. As a result, temperatures in these regions are extremely low, often approaching the faint background temperature of the universe itself. Without nearby galaxies or stars, there is nothing to disturb this equilibrium. Even within these voids, there are smaller structures known as dark nebulae and intergalactic clouds. These are remnants of gas and dust that have not yet formed into stars or been drawn into galaxies. They drift slowly through space, shaped only by gravity on the largest scales. In these regions, atoms exist in a state of extreme isolation. Collisions between particles are so rare that chemical processes occur at an incredibly slow pace, sometimes taking millions of years to complete even simple reactions. The temperature of these regions is not just a number. It reflects the lack of energy exchange. In environments where particles rarely interact, there is little opportunity for heat to spread. Instead, matter exists in a frozen-like state, not because it is solid, but because it is inactive. Motion continues, but at such low levels that change becomes almost imperceptible over short timescales. One of the most striking features of these starless regions is their silence in terms of radiation. Stars are the primary sources of visible light and energy in the universe. Without them, space becomes dark not only to the eye, but across much of the electromagnetic spectrum. In these voids, there are no bright signals, no energetic bursts, and no nearby sources of heat. The universe here is not just cold, it is dim and quiet in a fundamental sense. However, even in these seemingly empty regions, there is still a faint background presence. The cosmic microwave background radiation fills all of space, a remnant from the early universe, when everything was far hotter and denser. This radiation is extremely weak, but it provides a baseline temperature that prevents the universe from becoming completely devoid of heat. In starless regions, this background becomes the dominant source of energy, setting a minimal level of thermal activity. Despite their emptiness, these regions are not static. Over extremely long timescales, gravity continues to act. Small fluctuations in density can slowly grow, pulling matter together bit by bit. In some cases, this process eventually leads to the formation of new structures. A faint cloud of gas may gradually collapse, forming a new star system after billions of years. This slow evolution demonstrates that even the most inactive regions of the universe are still part of a larger dynamic system. The lack of stars in these regions also means the absence of heavy elements. Stars are the primary factories of chemical elements in the universe. Through nuclear fusion and supernova explosions, they create elements like carbon, oxygen, and iron. In starless regions, these processes do not occur locally. As a result, the composition of matter remains relatively simple, dominated by hydrogen and helium left over from the early universe. This simplicity reflects a universe in its most basic state. In some of the largest voids, known as supervoids, the scale of emptiness becomes almost incomprehensible. These structures can span hundreds of millions of light-years with very few galaxies inside them. From a cosmological perspective, they represent the opposite of galaxy clusters. Instead of dense regions filled with matter, they are vast expanses where matter is stretched thin across space. These supervoids are not completely empty, but they come close to being the closest thing to nothingness that exists on a cosmic scale. The cold within these regions is closely tied to their emptiness. Temperature in space is largely determined by particle interactions and radiation exposure. In areas where both are minimal, temperature naturally falls. However, unlike on Earth, where cold is often associated with dense matter like ice or snow, cosmic cold is associated with emptiness. It is a cold that comes from lack of interaction rather than presence of a cooling substance. In these environments, time itself feels different in a physical sense. While time continues to pass normally according to physics, the rate of change in matter is extremely slow. Without energy input, processes such as chemical reactions, molecular motion, and structural formation occur at minimal rates. This creates a universe where evolution is stretched across vast periods and where change is almost invisible on human timescales. The existence of these starless regions also provides important clues about the structure and evolution of the universe. Cosmologists study voids to understand how matter is distributed on the largest scales. These regions help reveal how galaxies form along filaments and how gravity shapes the cosmic web. In this way, emptiness becomes a source of information. By studying what is missing, scientists learn about what is present elsewhere. Interestingly, these voids are not completely uniform. Some contain faint structures, such as small groups of galaxies or isolated gas clouds. These remnants suggest that even in the most empty regions, the processes of cosmic evolution have left traces behind. Over time, gravitational forces may continue to pull matter into these areas, slowly reducing their emptiness. However, this process occurs over timescales far beyond human comprehension. The concept of starless regions also challenges intuitive ideas about space. On Earth, emptiness is often associated with simplicity. A room with no objects is easy to understand. In the universe, however, emptiness is complex. It is not a simple absence, but a state defined by extremely low density, weak interactions, and minimal energy flow. Even nothingness in space is structured by physical laws. In some theoretical models, these voids may play a role in the long-term evolution of the universe. As galaxies move and cosmic expansion continues, voids may grow larger. Matter may become increasingly concentrated into smaller regions, leaving more space between structures. In this scenario, the universe could gradually shift toward a state dominated by emptiness, with isolated galaxies drifting farther apart over time. Despite this, even the emptiest regions are still part of the cosmic system. They are not outside the universe, but within it, shaped by the same forces that govern everything else. Gravity, expansion, and quantum fluctuations all continue to operate even in the absence of visible structures. This means that no part of the universe is truly disconnected from the whole. From a philosophical perspective, these starless cold regions offer a different kind of reflection on existence. They show that much of the universe is not filled with activity or light, but with silence and stillness. Life exists in a narrow band between extremes, surrounded by vast regions that are uninhabitable and inactive. This perspective highlights how rare and fragile habitable conditions truly are. At the same time, these regions remind us that the universe is not defined only by what is visible. Much of its structure is invisible, shaped by forces that operate without direct observation. Dark matter, cosmic expansion, and gravitational interactions all influence these regions, even if they cannot be seen directly. The universe is therefore both visible and invisible, active and quiet, full and empty at the same time. The study of these cold, starless regions continues to be an important part of modern astrophysics. By mapping cosmic voids and analyzing their properties, scientists gain insight into the early universe, the distribution of matter, and the nature of cosmic evolution. These regions act as natural laboratories for understanding how structure emerges from near emptiness. As our exploration of the universe continues, these voids serve as a reminder that not all important places are bright or active. Some of the most significant parts of the cosmos are defined by their silence. In their stillness, they preserve the history of cosmic evolution and provide a backdrop against which all other activity takes place. In the next stage of our journey, we will move from these silent, starless regions into environments of extreme heat and energy, where matter behaves in completely different ways and the universe reveals its most violent and dynamic side. If cold represents stillness and silence in the universe, then heat represents motion, violence, and transformation on a scale that defies imagination. In the heart of stars, matter is pushed to its limits, crushed and heated until atoms are stripped apart and rebuilt in constant cycles of nuclear fusion. These stellar furnaces are not gentle sources of light. They are engines of creation powered by destruction, where temperatures reach millions of degrees and the rules of ordinary chemistry no longer apply. To understand the hottest stars in the universe, it is important to begin with the basic process that powers them. Stars exist because of a balance between gravity and pressure. Gravity constantly pulls matter inward, trying to collapse the star under its own weight. At the same time, nuclear fusion in the core releases energy that pushes outward. This balance keeps a star stable for most of its life, but the intensity of this process depends on the mass of the star. The more massive the star, the more extreme the conditions inside it become. In the largest and most powerful stars, temperatures in the core can reach tens of millions of degrees. At these levels, hydrogen atoms collide with such force that they fuse into helium, releasing enormous amounts of energy. This energy travels outward, heating the surrounding layers of the star. In more massive stars, this process continues beyond helium, creating heavier and heavier elements. Carbon, oxygen, neon, silicon, and eventually iron can all be formed in the cores of the most extreme stars. However, as stars become more massive and hotter, their lifespans become shorter. This is because they burn through their fuel at an incredibly rapid rate. A small, stable star like the Sun can shine for billions of years, but the most massive stars in the universe may only live for a few million years, a brief moment in cosmic time. Their intense heat is both their power and their downfall. The surface temperatures of the hottest stars can also be extreme. Some stars have surface temperatures exceeding 50,000 degrees Celsius, far hotter than the Sunday. These stars emit large amounts of ultraviolet radiation and appear blue or blue-white in color. Their intense energy output affects surrounding space, ionizing nearby gas and shaping the environment around them. Beyond ordinary massive stars, there are even more extreme stellar objects. Some stars enter phases where their internal processes become unstable, causing rapid changes in temperature and brightness. These unstable stars can eject massive amounts of material into space, creating shock waves and heating surrounding regions to extreme levels. In these moments, the star becomes a source of both creation and destruction, scattering elements across space while briefly reaching incredible energy outputs. When the most massive stars reach the end of their lives, they do not fade quietly. Instead, they explode in some of the most violent events in the universe, known as supernovae. During a supernova, the core of the star collapses in seconds, while the outer layers are blasted outward at incredible speeds. Temperatures during this process rise to billions of degrees, creating conditions so extreme that new elements are forged in the explosion itself. These supernova events are among the most important processes in the universe. Without them, heavy elements like gold, uranium, and platinum would not exist. The explosion scatters these elements across space, where they eventually become part of new stars, planets, and even living organisms. In this way, the heat of dying stars becomes the foundation for new cosmic structures. The regions surrounding supernovae are among the most dangerous in the universe. The shock waves from the explosion heat nearby gas to extreme temperatures, sometimes creating expanding shells of plasma that glow intensely across the electromagnetic spectrum. Radiation levels in these regions are lethal to any nearby planets or systems. If a supernova occurs too close to a planetary system, it can strip away atmospheres and sterilize surfaces completely. Beyond individual stars, there are environments where heat reaches even more extreme levels. In the centers of galaxies, supermassive black holes often dominate the environment. While black holes themselves do not emit light or heat directly, the matter falling into them forms accretion disks that heat up to incredible temperatures due to friction and gravitational forces. These disks can reach millions of degrees and emit powerful radiation, making them some of the brightest objects in the universe. In active galactic nuclei, where supermassive black holes are feeding on large amounts of matter, the energy output can be so intense that it outshines the entire galaxy surrounding it. These regions are not only hot, but also highly energetic and dynamic. Jets of particles can be ejected at nearly the speed of light, stretching across thousands of light years and heating intergalactic space along their paths. Even within our own galaxy, there are regions of extreme heat and energy. Star-forming regions where new stars are being born are filled with hot gas and dust compressed by gravity. As these regions collapse, temperatures rise, triggering nuclear fusion and the birth of new stars. These stellar nurseries are often chaotic environments, where shock waves from young stars interact with surrounding material, creating complex and dynamic structures. Heat in the universe is not only produced by stars and black holes, it is also generated by collisions and interactions on massive scales. When galaxies collide, enormous amounts of gas are compressed and heated. These galactic collisions do not happen quickly in human terms, but over millions of years they reshape entire systems. The heat generated during these interactions can trigger waves of star formation, transforming the structure of galaxies. On smaller scales, even planets can experience extreme heat. Some planets orbit so close to their parent stars that their surfaces reach temperatures high enough to melt rock. These worlds, often referred to as lava planets, have surfaces that are partially or completely molten. The intense radiation from their stars strips away atmospheres and continuously heats their surfaces, creating environments of constant geological activity. In some cases, tidal forces from nearby massive objects can also generate internal heat within planets or moons. As these bodies are stretched and compressed by gravity, friction inside their interiors produces heat. This process can lead to volcanic activity even in regions far from stellar heat sources. This shows that heat in the universe can come from multiple sources, not just radiation from stars. At the extreme end of cosmic temperatures are conditions that existed shortly after the Big Bang. In the earliest moments of the universe, everything was incredibly hot and dense. Temperatures were so high that particles could not form stable atoms. Matter existed in a plasma-like state, where energy and particles were constantly interacting. As the universe expanded, it began to cool, allowing matter to form and structure to develop. This early state of the universe represents the hottest conditions ever known. It was a time when the fundamental forces of nature behaved differently, and the distinction between energy and matter was not as clear as it is today. Understanding this period helps scientists learn how the universe evolved from a uniform state into the complex structure we observe now. Heat in the universe is closely connected to energy flow and transformation. Wherever there is intense heat, there is also rapid change. Stars are born, evolve, and die through processes driven by heat. Galaxies form and collide, shaped by energetic interactions. Even the distribution of matter on the largest scales is influenced by thermal processes from the early universe. Despite its destructive nature, heat is essential for cosmic evolution. Without it, there would be no stars, no elements, and no complexity. Heat drives the cycles of creation and destruction that shape the universe. It transforms simple hydrogen into complex elements, and it powers the engines of galaxies. However, heat also has limits. At extremely high temperatures, matter behaves in ways that challenge our understanding of physics. At the cores of stars, and in extreme astrophysical events, atoms break down, and particles interact in ways that require advanced theories to describe. These conditions provide important testing grounds for modern physics, helping scientists refine their understanding of the universe. In contrast to the cold, silent regions of space, the hottest environments are filled with energy, motion, and transformation. They are places where the universe is most active, constantly changing and evolving. These extremes of heat reveal the dynamic side of the cosmos, showing that the universe is not static, but always in motion. As we continue to explore the universe, understanding these extreme temperatures helps us understand the full range of cosmic behavior. From the coldest voids to the hottest stars, the universe exists as a balance between stillness and energy. Heat represents one side of this balance, driving change and creation across vast distances. In the next stage of our journey, we will move beyond stars into even more extreme environments, where gravity itself becomes the dominant force and the fabric of space and time begins to break down. When a star reaches the end of its life, the universe does not simply let it fade away quietly. Instead, in many cases, it transforms that star into one of the most violent and energetic events known to science. A supernova is not just an explosion in space. It is a total collapse and rebirth of matter on a scale so large that it briefly outshines entire galaxies. In those moments, the universe reveals one of its most destructive and creative forces at the same time. To understand supernova death zones, we must first understand what leads a star to this final moment. Throughout its life, a star exists in a delicate balance between gravity pulling inward and nuclear fusion pushing outward. This balance defines stability, but as a star ages, its internal fuel begins to change. Hydrogen is gradually converted into heavier elements like helium, carbon, oxygen, and beyond. In smaller stars, this process can continue in a controlled way for billions of years. But in massive stars, the story is very different. Large stars burn their fuel at an extremely fast rate. Their cores become hotter and denser, fusing elements in a rapid sequence that builds heavier and heavier atomic structures. Eventually, the star reaches a point where it begins producing iron in its core. Iron is a turning point in stellar evolution because it does not release energy through fusion. Instead, it absorbs energy. At this stage, the star can no longer sustain the outward pressure needed to resist gravity. Once this balance is lost, collapse begins almost instantly. The core of the star is crushed inward under its own weight in a fraction of a second. Temperatures rise dramatically, reaching billions of degrees. Electrons are forced into protons, forming neutrons, and the core becomes incredibly dense. In many cases, this collapse forms either a neutron star or a black hole, depending on the mass of the original star. While the core collapses inward, the outer layers of the star behave in a completely different way. They are thrown outward in a massive explosion that releases more energy in seconds than the Sun will produce in its entire lifetime. This is the supernova explosion. It is one of the most powerful events in the universe, and it transforms everything around it. The energy released during a supernova is so extreme that it affects space on a massive scale. Shock waves travel outward at thousands of kilometers per second, heating surrounding gas and dust to extremely high temperatures. In these regions, matter is stripped of electrons, forming a hot plasma that glows across multiple wavelengths of light. These expanding clouds of debris create what is known as a supernova remnant. A supernova remnant is not just a leftover shell of an explosion. It is a dynamic and evolving structure. As the shock wave moves outward, it interacts with interstellar material, compressing and heating it. This can trigger the formation of new stars in nearby regions, meaning that the death of one star can contribute to the birth of many others. In this way, supernovae are deeply connected to the cycle of creation in the universe. However, the immediate environment of a supernova is extremely dangerous. In the moments following the explosion, radiation levels spike to lethal levels. Gamma rays, X-rays, and high-energy particles flood the surrounding space. Any planet located too close to the explosion would be exposed to radiation strong enough to strip away its atmosphere and destroy any potential life on its surface. The distance at which a supernova becomes dangerous depends on its energy and type, but even relatively distant events can have significant effects. If a supernova were to occur within a few dozen light-years of Earth, it could potentially disrupt the planet's ozone layer, increasing radiation exposure at the surface. Fortunately, such events are extremely rare in our galactic neighborhood. Inside the expanding supernova remnant, temperatures remain extremely high for thousands of years. As the shockwave expands, it continues to heat surrounding gas, maintaining a hot and turbulent environment. Over time, the remnant cools and disperses, enriching the interstellar medium with heavy elements created during the star's life and death. These elements become part of future star systems, planets, and eventually biological life. One of the most important contributions of supernovae is the creation of heavy elements. Elements like gold, silver, uranium, and many others are formed during the extreme conditions of the explosion. The intense pressure and temperature allow atomic nuclei to capture neutrons rapidly, forming elements heavier than iron. This process is known as nucleosynthesis, and it is one of the key ways the universe builds complexity. Without supernovae, the universe would be composed mostly of hydrogen and helium. There would be no rocky planets, no complex chemistry, and no life as we know it. In this sense, supernova death zones are not just destructive regions, they are essential for the chemical evolution of the universe. As the shock wave from a supernova travels through space, it creates regions of intense turbulence. Gas clouds are compressed, heated, and reshaped by the passing energy. In some cases, this compression triggers the collapse of nearby gas clouds, leading to the formation of new stars. This means that supernovae can act as catalysts for star formation, influencing entire regions of a galaxy. The structure of a supernova remnant changes over time. In the early stages, the explosion is highly energetic and fast-moving. The shock wave expands rapidly, carrying most of the energy outward. As it interacts with surrounding material, it begins to slow down and spread out. Eventually, the remnant becomes a diffuse cloud of gas and dust, gradually mixing with the interstellar medium. Even in its later stages, a supernova remnant can remain extremely hot compared to surrounding space. The temperatures inside these regions can still reach millions of degrees, especially in areas where shock waves collide with dense material. This creates complex structures filled with filaments, knots, and bubbles of hot plasma. Some of the most famous supernova remnants in our galaxy are studied extensively by astronomers. These remnants provide valuable information about the life cycles of stars and the distribution of elements in the universe. By analyzing the light and radiation emitted from these regions, scientists can determine the composition, temperature, and velocity of the expanding material. Supernova death zones are also important in shaping the structure of galaxies. The energy released during these explosions can push gas and dust across large distances, influencing the formation of spiral arms and other galactic features. Over time, repeated supernova events contribute to the dynamic and evolving nature of galaxies. In addition to single-star supernovae, there are also binary star systems that can produce similar explosive events. In some cases, a dense white dwarf star can accumulate material from a companion star until it reaches a critical limit and explodes in a type of supernova known as a type Ia. These events are particularly important in astronomy because they have consistent brightness, allowing scientists to measure distances across the universe. The study of supernova death zones also provides insight into the behavior of matter under extreme conditions. Temperatures, pressures, and densities in these environments are far beyond anything that can be reproduced on Earth. This makes supernovae natural laboratories for studying physics at its most extreme limits. Despite their destructive nature, supernovae are essential to the evolution of the universe. They distribute elements, trigger star formation, and influence the structure of galaxies. Without them, the universe would remain chemically simple and structurally less diverse. Their explosive energy drives change on a cosmic scale. The concept of a death zone in a supernova is not limited to the explosion itself. It also includes the surrounding region affected by the event. This zone can extend for many light years, depending on the strength of the explosion. Within this region, radiation levels remain elevated, and the environment is shaped by the aftermath of the blast. Over time, These death zones evolve into regions of renewal. As radiation levels decrease and temperatures cool, new stars begin to form from the enriched material left behind. These new stars may eventually develop planetary systems, continuing the cycle of cosmic evolution. In this way, destruction becomes a necessary step in creation. Supernovae also play a role in distributing elements across the galaxy. The material ejected during the explosion spreads outward, mixing with interstellar gas. This process ensures that heavy elements are not confined to a single location, but are spread throughout the galaxy. This distribution is essential for the formation of diverse planetary systems. From a broader perspective, supernova death zones represent one of the most dramatic examples of transformation in the universe. They show how endings and beginnings are closely connected. A single star's death can influence the formation of countless new structures, shaping the future of entire regions of space. In the grand cycle of the universe, supernovae are both destroyers and creators. They mark the end of stellar life, but also enable the continuation of cosmic evolution. Their energy reshapes space, their material builds new worlds, and their influence extends far beyond the moment of explosion. As we continue to explore the universe, supernova death zones remain key areas of study. They reveal the processes that drive change on the largest scales and help us understand how the elements of life are formed and distributed. They remind us that even in the most violent events, there is structure, purpose, and continuity. In the next stage of our journey through the extremes of the universe, we will move beyond explosive stars into the realm of objects where gravity itself becomes the dominant force, bending space and time into forms that challenge the limits of understanding. In the universe, gravity is the silent architect behind almost everything that exists. It pulls matter together to form stars, shapes galaxies into vast spirals and clusters, and even governs the orbits of planets around their suns. But in some regions of space, gravity becomes so extreme that it stops being just a force of attraction and instead becomes something far more profound. It begins to dominate space itself. In these places, the structure of reality is altered in ways that defy ordinary understanding. These are the realms of black holes. A black hole is formed when an enormous amount of mass is compressed into an incredibly small region of space. This typically happens at the end of a massive star's life, after it has already gone through a supernova explosion. If the remaining core of the star is heavy enough, no known force in nature can stop it from collapsing under its own gravity. The result is a point of infinite density, known as a singularity, surrounded by a boundary called the event horizon. The event horizon is not a physical surface. It is a limit in space beyond which nothing can escape. Once matter or light crosses this boundary, it is pulled inward forever, unable to return. This is why black holes appear completely dark. They do not emit light, and they do not reflect it. Instead, they absorb everything that comes too close. The region surrounding a black hole is one of the most extreme environments in the universe. As matter approaches the event horizon, it is stretched and compressed by gravitational forces in a process often referred to as spaghettification. The difference in gravitational pull between the near side and far side of an object becomes so extreme that it is pulled apart at the atomic level. This creates a zone of intense destruction where matter is broken down into its most basic components. Before crossing the event horizon, matter often forms a rotating disk known as an accretion disk. This disk is made up of gas, dust, and debris spiraling inward toward the black hole. As the material moves faster and closer to the event horizon, it collides with itself, generating immense friction. This friction heats the disk to extreme temperatures, sometimes reaching millions of degrees. At these temperatures, the accretion disk becomes one of the brightest sources of radiation in the universe. In fact, even though black holes themselves are invisible, their surroundings can shine brilliantly. The energy released from accretion disks can outshine entire galaxies. These active regions are known as quasars, or active galactic nuclei, when associated with supermassive black holes at the centers of galaxies. The light they emit is not coming from the black hole itself, but from the violent heating of matter before it disappears beyond the event horizon. Black holes come in different sizes. Stellar black holes form from collapsed stars and can be several times the mass of our Sun. Supermassive black holes, on the other hand, exist at the centers of most galaxies and can contain millions or even billions of solar masses. The origin of these enormous black holes is still an area of active research, but they are known to play a central role in the structure and evolution of galaxies. The environment near a supermassive black hole is particularly extreme. Stars orbit at incredible speeds, sometimes completing full orbits in just a few years or even months. The gravitational forces are so strong that they can distort the shapes of nearby stars and influence the movement of entire star clusters. In some cases, stars that stray too close are torn apart and absorbed, adding to the black hole's mass. One of the most fascinating aspects of black holes is their effect on time. According to the theory of relativity, time slows down in stronger gravitational fields. Near the event horizon of a black hole, this effect becomes extremely pronounced. To an outside observer, an object falling into a black hole appears to slow down and fade away as it approaches the event horizon. From the perspective of the falling object, however, time continues normally until it crosses the boundary. This difference in perception creates one of the most mysterious aspects of black holes. Time itself becomes relative to position and gravity. In extreme cases, time near a black hole can slow to such an extent that seconds near the event horizon correspond to years or even centuries farther away. This makes black holes not only regions of extreme gravity, but also regions where the flow of time is fundamentally altered. Inside the event horizon, our current understanding of physics begins to break down. The singularity at the center of a black hole is a point where density becomes infinite and the known laws of physics no longer apply. At this point, space and time, as we understand them, cease to function in a predictable way. Scientists believe that a complete theory of quantum gravity will be needed to fully describe what happens in this region. Despite their destructive nature, black holes are not simply cosmic vacuum cleaners that endlessly consume everything around them. They have a limited influence, based on their mass and distance. If the Sun were replaced by a black hole of the same mass, the Earth would continue to orbit it normally at the same distance. The danger of black holes lies in approaching them too closely, not in their mere existence. Black holes also play an important role in shaping galaxies. Supermassive black holes at galactic centers influence the motion of stars and gas, helping to stabilize or reshape galactic structures over time. Their gravitational pull affects star formation rates and can regulate the growth of galaxies by controlling how much matter is available for new stars. In some cases, black holes can also produce powerful jets of energy. These jets are streams of particles accelerated to nearly the speed of light, ejected along the poles of the black hole's rotation. They can extend for thousands of light years, carrying enormous amounts of energy into intergalactic space. These jets interact with surrounding matter, heating and shaping the environment on large scales. The regions surrounding black holes are therefore not empty voids, but highly dynamic environments filled with energy, radiation, and extreme gravitational effects. Matter behaves in unusual ways under these conditions, and even light is affected. The bending of light around black holes, known as gravitational lensing, allows astronomers to observe distorted images of background stars and galaxies. Black holes also challenge our understanding of information in the universe. According to classical physics, information about matter that falls into a black hole is lost forever. However, modern theoretical work suggests that information may be preserved in some form, possibly encoded on the surface of the event horizon or released through subtle radiation processes. This is known as the black hole information paradox and remains one of the most important unsolved problems in physics. Another key concept related to black holes is Hawking radiation, a theoretical prediction that black holes can slowly lose energy over time. According to this idea, quantum effects near the event horizon allow black holes to emit small amounts of radiation. Over extremely long timescales, this could cause black holes to evaporate completely. However, for most black holes in the universe, this process would take far longer than the current age of the universe. The study of black holes has transformed our understanding of gravity, space, and time. They are no longer seen as simple destructive objects, but as essential components of cosmic structure. They reveal the limits of physical laws and provide clues about the deeper nature of reality. In a broader sense, black holes represent one of the most extreme expressions of gravity in the universe. They show what happens when matter is pushed beyond the limits of stability, when space itself is curved to its most extreme form, and when time becomes relative to position. They are not just objects in space, but regions where the fabric of the universe is fundamentally altered. Despite their terrifying reputation, black holes are not rare anomalies. They exist throughout the universe, from small stellar remnants to the enormous central engines of galaxies. Their presence is a natural outcome of stellar evolution and gravitational collapse. In this way, they are an integral part of the cosmic cycle. As we continue to explore the universe, black holes remain some of the most important objects of study. They push the boundaries of physics and challenge our understanding of reality. They connect the largest scales of galaxies with the smallest scales of quantum mechanics acting as bridges between different realms of science. In the next stage of our journey through the extremes of the universe, we will move from the deep gravitational wells of black holes into the dense and magnetic remnants of stars, where matter exists in forms that are even more compact and extreme, continuing the story of cosmic transformation. In the aftermath of a supernova explosion, not every star ends its life by collapsing into a black hole. Some stars leave behind a different kind of remnant, one that is smaller in size than almost anything else in the universe, but contains more mass than the Sunday. These remnants are known as neutron stars, and they represent one of the most extreme states of matter ever discovered. In these objects, atoms no longer exist in their normal form, and matter is compressed into a state that challenges the limits of physics. A neutron star is formed when a massive star undergoes a supernova explosion, and its core collapses under gravity. If the remaining core is not heavy enough to become a black hole, it compresses into a sphere only about 10 to 20 kilometers in diameter. Despite its small size, it can contain up to twice the mass of the Sunday. This means that a neutron star has an incredibly high density, where a single teaspoon of its material would weigh billions of tons if brought to Earth. The process that creates a neutron star begins with the collapse of atomic structure. Under normal conditions, atoms are mostly empty space with electrons orbiting a nucleus. But in the core of a collapsing star, pressure becomes so extreme that electrons are forced into protons. When this happens, they combine to form neutrons. As a result, the entire core becomes a tightly packed sphere of neutrons with almost no empty space between them. This transformation creates a new state of matter that does not exist naturally on Earth. Neutron stars are essentially giant atomic nuclei, held together not by chemical bonds, but by the strong nuclear force. Gravity compresses this matter to the point where quantum mechanical effects become dominant on a macroscopic scale. The result is an object that is incredibly dense, stable, and strange in its behavior. The surface of a neutron star is unlike anything found in the solar system. It is extremely hot, with temperatures reaching hundreds of thousands or even millions of degrees. The gravity at the surface is so strong that it dramatically alters the structure of matter. If a human were somehow placed on the surface of a neutron star, they would be instantly crushed and vaporized, not just by pressure, but by the extreme forces acting on individual atoms. Neutron stars also have extremely strong gravitational fields. While they are not as extreme as black holes, their gravity is still powerful enough to significantly affect nearby objects. If a spacecraft were to approach too closely, it would experience intense tidal forces that could tear it apart. Even light is affected by this gravity, which causes the surface of a neutron star to appear distorted when observed from a distance. One of the most fascinating features of neutron stars is their rotation. When a massive star collapses into a neutron star, its rotation speed increases dramatically due to the conservation of angular momentum. This is similar to how a spinning ice skater rotates faster when pulling in their arms. As a result, neutron stars can rotate extremely quickly, sometimes completing hundreds of rotations per second. These rapidly rotating neutron stars are known as pulsars. Pulsars emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If one of these beams is aligned with Earth, it can be detected as a regular pulse of radiation. This regularity is so precise that pulsars are among the most accurate natural clocks in the universe. The magnetic fields of neutron stars are also extremely powerful. In some cases, they are trillions of times stronger than Earth's magnetic field. These ultra-strong magnetic neutron stars are known as magnetars. The magnetic energy stored in these objects is so intense that it can distort atomic structures and affect the vacuum of space itself. If a magnetar were located at a relatively close distance to Earth, its magnetic field could disrupt electronics and potentially strip information from atoms. Magnetars are also capable of producing powerful bursts of energy known as starquakes. The crust of a neutron star, although extremely strong, can still experience stress due to magnetic and rotational forces. When this crust suddenly shifts or cracks, it releases enormous amounts of energy in a very short time. These bursts can be detected across vast distances in space and are among the most energetic events in the universe after supernovae. The interior of a neutron star is even more extreme than its surface. As one moves deeper, pressure increases to levels that are difficult to fully understand with current physics. The matter inside is believed to exist in exotic forms, where neutrons are packed so tightly that they may break down into even smaller particles. Some theories suggest that the core of a neutron star may contain strange matter or other exotic states that are not yet fully understood. Despite their extreme nature, neutron stars are relatively stable compared to other cosmic objects. Once formed, they can exist for billions of years, slowly cooling and rotating. Over time, their magnetic fields weaken and their emissions fade. Eventually, they may become nearly invisible, drifting through space as cold, dense remnants of once massive stars. Neutron stars often exist in binary systems where they orbit another star or even another neutron star. In these systems, interactions between the two objects can lead to dramatic phenomena. If a neutron star pulls material from a companion star, it can create bright X-ray emissions as the material is heated to extreme temperatures during accretion. These systems are some of the brightest X-ray sources in the sky. When two neutron stars collide, the result is one of the most powerful events in the universe. This collision, known as a kilonova, releases enormous amounts of energy and produces heavy elements such as gold and platinum. The gravitational waves generated by these events ripple through space-time and can be detected by specialized observatories on Earth. These collisions are not only spectacular but also scientifically important, as they help explain the origin of many heavy elements in the universe. The study of neutron stars also provides insight into the behavior of matter under extreme conditions. Because their interiors cannot be directly observed, scientists use mathematical models and astronomical observations to understand their structure. These studies help refine theories of nuclear physics and quantum mechanics, making neutron stars important natural laboratories for extreme physics. One of the key questions in neutron star research is how matter behaves at such extreme densities. At the core, pressure is so high that normal atomic structures cannot exist. The exact state of matter under these conditions is still unknown. Some models suggest a fluid of neutrons, while others propose more exotic forms of matter involving quarks and gluons. Understanding this state of matter is one of the major challenges in modern astrophysics. Neutron stars also play an important role in the evolution of galaxies. As they move through space, they can interact with surrounding gas and dust, influencing the distribution of matter. Their magnetic fields and radiation emissions can also affect nearby environments, contributing to the complex dynamics of the interstellar medium. From a broader perspective, neutron stars represent a transition point between ordinary matter and the most extreme objects in the universe. They exist at the boundary between stability and collapse, between atomic structure and complete gravitational domination. In this sense, they are one of the most important links in the chain of cosmic evolution. The existence of neutron stars also raises deeper questions about the limits of matter. If atoms can be crushed into neutrons, and neutrons can potentially break down further, what is the ultimate limit of compression? This question connects neutron stars to the study of black holes and the fundamental structure of the universe. In the cosmic scale of extremes, neutron stars occupy a unique position. They are not as large as black holes, but they are far denser than any normal star. They are not as energetic as supernovae, but they are remnants of those explosions. They are stable, yet filled with extreme conditions that push the boundaries of physics. As we continue to explore the universe, neutron stars remain one of the most important objects of study. They help us understand how matter behaves under pressure, how stars evolve and die, and how elements are formed and distributed across space. They also serve as natural laboratories for testing the limits of physical laws. In the next stage of our journey through the universe's extremes, we will move from these dense stellar remnants into planetary environments of fire and radiation, where entire worlds are shaped by heat, volcanism, and intense cosmic forces that transform them into some of the most hostile places known to science. Not all extreme environments in the universe are shaped by stars that have died or collapsed. Some of the most hostile worlds are still active, still evolving, and still being reshaped by powerful internal and external forces. These are planets and moons where heat, gravity, and radiation combine to create surfaces that are constantly changing, unstable, and often violently active. They are volcanic hellscapes, worlds where the ground itself is in motion and where destruction is part of the normal state of existence. In our own solar system, one of the most extreme examples of volcanic activity exists on Jupiter's moon Io. At first glance, Io might seem like a small, distant moon, but its surface tells a very different story. It is the most volcanically active body in the entire solar system. Unlike Earth, where volcanic activity is driven mainly by internal heat, Io's extreme volcanism is powered by gravitational forces. Io orbits extremely close to Jupiter, one of the largest planets in the solar system. It is also influenced by the gravitational pull of nearby moons. These competing forces constantly stretch and compress Io's interior in a process known as tidal heating. As Io flexes under this gravitational stress, friction inside its interior generates enormous amounts of heat. This heat has no easy way to escape, except through volcanic eruptions on the surface. As a result, Io is covered in hundreds of active volcanoes. These volcanoes erupt continuously, releasing sulfur-rich lava that spreads across the surface in bright, colorful flows. The landscape is constantly being reshaped, with new lava plains forming while older regions are buried or destroyed. Some volcanic plumes on Io rise hundreds of kilometers into space, ejecting material far above the Moon's surface before it falls back down. The colors of Io are also a reflection of its extreme environment. The surface is covered in shades of yellow, red, orange, and black, created by sulfur compounds at different temperatures. These colors are not static. They change over time as volcanic activity reshapes the surface. Io is not a frozen world. It is a constantly changing one, where geology is active on a global scale. While Io is a moon, there are also planets in the universe that exist under similar or even more extreme conditions. Some planets orbit so close to their stars that their surfaces are permanently heated to extreme temperatures. These worlds are often referred to as lava planets. On these planets, the surface is not solid in the traditional sense. Instead, it is partially or completely molten, with vast oceans of lava covering large portions of the surface. On lava planets, the side facing the star can reach temperatures high enough to melt rock into liquid. The heat is so intense that any atmosphere present may be partially vaporized or constantly replenished by volcanic activity. The result is a world where the surface is in a constant state of motion, with molten rock flowing, cooling, and reheating in a continuous cycle. The boundary between day and night on these planets can be extreme. The side facing the star is blisteringly hot, while the opposite side may be significantly cooler. This temperature difference can drive strong winds of vaporized rock, creating dynamic atmospheric circulation systems unlike anything on Earth. Even more extreme environments can be found on planets orbiting highly active stars. Some stars emit intense radiation and flares that bombard nearby planets with constant energy. These radiation-rich environments can strip away atmospheres and heat planetary surfaces to extreme levels. In some cases, the radiation is so strong that it prevents stable surface conditions from forming at all. In addition to stellar heating, some planetary bodies are influenced by internal radioactive decay. Elements within a planet's interior slowly release energy as they decay, producing heat over long periods of time. When combined with gravitational forces and external radiation, this internal heat can contribute to intense volcanic activity. On Earth, volcanism is relatively localized and intermittent. In contrast, volcanic hellscapes in the universe can be global and continuous. Entire planetary surfaces can be reshaped by ongoing eruptions, with lava flows covering vast regions. In some cases, volcanic activity can even dominate the atmosphere, releasing gases that alter the chemical composition of the surrounding environment. These volcanic environments are not limited to rocky planets. Even icy worlds in the outer regions of solar systems can experience cryovolcanism, where instead of molten rock, substances like water, ammonia, or methane erupt as liquid or vapor due to internal heat. While these are colder processes, they are still driven by similar physical mechanisms and represent another form of planetary activity. In many extreme worlds, the interaction between heat and gravity plays a central role. Planets that are too close to their stars can become tidally locked, meaning one side always faces the star while the other remains in darkness. This creates extreme temperature differences between the two hemispheres, further contributing to atmospheric instability and surface activity. In some cases, the constant heating of a planet's surface can lead to runaway geological processes. As materials melt and flow, they can expose deeper layers of the planet, releasing additional heat and volatile compounds. This creates feedback loops that sustain long-term volcanic activity. Volcanic hellscapes also exist beyond individual planets. Entire moons, dwarf planets, and even large asteroids can experience volcanic or cryovolcanic activity depending on their composition and internal structure. The key factor is energy balance. If a body can retain or generate enough internal heat, it can remain geologically active even in the cold outer regions of a solar system. The study of these extreme environments helps scientists understand how planets evolve over time. Volcanism plays a crucial role in shaping planetary surfaces, creating atmospheres, and recycling materials between a planet's interior and exterior. Without volcanic activity, many planets would be geologically dead, with no mechanism to renew their surfaces or atmospheres. In the context of the universe, volcanic hellscapes represent a form of energetic balance between destruction and renewal. Lava flows destroy existing landscapes but also create new ones. Eruptions release gases that can form atmospheres, but they can also strip them away. This constant cycle of change makes these worlds some of the most dynamic environments known. From a broader perspective, these extreme volcanic worlds also help us understand the limits of planetary habitability. While they are far too hostile for life as we know it, they demonstrate the wide range of conditions that planets can experience. They show that planetary systems are not static, but constantly evolving under the influence of internal and external forces. Some of the most extreme volcanic environments may also exist outside our solar system. Exoplanets orbiting very close to their stars, known as ultra-hot planets, may have surfaces that are partially vaporized. In these environments, rock itself can exist as gas due to extreme temperatures. This creates atmospheres made of vaporized minerals, constantly shifting under intense heat and radiation. These exotic worlds challenge our understanding of what a planet can be. They blur the line between solid and gaseous states, between surface and atmosphere, and between stability and chaos. In these environments, traditional geological processes operate under entirely different rules. Despite their extreme nature, volcanic hellscapes are important to the overall structure of planetary systems. They help redistribute energy, recycle materials, and influence the long-term evolution of planets. Even in their most destructive forms, they are part of a larger cosmic system of balance and change. As we study these environments, we gain insight into how diverse planetary systems can be. Not all worlds are calm or stable. Many are shaped by forces that are constantly active, reshaping their surfaces and atmospheres over time. These worlds remind us that the universe is not uniform, but filled with a wide range of conditions. In the broader story of cosmic extremes, volcanic hellscapes represent the intense interaction between heat, gravity, and matter on planetary scales. They show how energy from stars and internal planetary processes can combine to create environments of continuous transformation. As we continue our journey through the extremes of the universe, we will move from these fiery worlds into regions dominated not just by heat or gravity, but by invisible forces of radiation and energy that shape space itself on even larger scales. Across the universe, there are regions where the most dangerous force is not heat, not cold, and not even gravity in its most extreme form. Instead, it is invisible energy, moving at the speed of light, carrying enough power to strip atoms apart and alter the very structure of matter. This is radiation, and in certain cosmic environments, it becomes so intense that it defines the nature of space itself. These are the radiation zones of the cosmos, regions where survival as we understand it is impossible, and where even the fabric of reality is constantly under assault. Radiation in space comes in many forms. It can be electromagnetic, such as gamma rays and X-rays, or it can be particle-based, such as high-energy protons and cosmic rays. On Earth, our atmosphere and magnetic field protect us from most of this radiation. Without that protection, life would not be possible on the surface. But in deep space, far from planetary shields, radiation is everywhere. It flows through galaxies, erupts from stars, and streams from the centers of black holes. One of the most powerful sources of radiation in the universe is the active galactic nucleus. At the center of many galaxies lies a supermassive black hole surrounded by a swirling accretion disk of gas and dust. As matter falls toward the black hole, it heats up to extreme temperatures, emitting intense radiation across the entire electromagnetic spectrum. In some cases, this output becomes so powerful that it outshines the entire galaxy in which it resides. These active galactic nuclei are not quiet or stable environments. They are dynamic and violent, constantly consuming matter and releasing energy. The radiation produced in these regions can extend across thousands of light years, affecting everything in its path. Any nearby star systems would be exposed to levels of energy far beyond what is found in calmer regions of a galaxy. In addition to radiation from accretion disks, many of these systems produce powerful jets of particles. These jets are narrow beams of charged particles that are accelerated to nearly the speed of light and ejected along the poles of the black hole's rotation. They travel vast distances through space, sometimes stretching far beyond the boundaries of their host galaxies. As they move, they interact with interstellar and intergalactic material, heating and ionizing it along their path. Another major source of cosmic radiation is the pulsar. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the star spins, These beams sweep across space like the beam of a lighthouse. When aligned with Earth, they can be detected as regular pulses of radiation. While pulsars are extremely precise cosmic clocks, they are also intense sources of high-energy radiation. The environment around a pulsar is extremely hostile. The magnetic fields are so strong that they accelerate particles to incredible energies. Radiation levels near these objects are lethal to any form of known life. Even at a distance, the energy output can influence surrounding space, affecting gas clouds and nearby celestial bodies. Supernova remnants are another important source of radiation in the universe. When a massive star explodes, it releases enormous amounts of energy in the form of light, X-rays, and gamma rays. The expanding shock wave from the explosion continues to heat surrounding material for thousands of years. During this time, the remnant remains a strong source of radiation, shaping the interstellar environment around it. Cosmic rays also contribute to the radiation environment of the universe. These are high-energy particles that travel through space at nearly the speed of light. Their origins are diverse, including supernovae, active galaxies, and other energetic events. When these particles collide with matter, they can produce secondary radiation and initiate complex particle interactions. On Earth, cosmic rays constantly bombard the atmosphere, but most are blocked before reaching the surface. In deep space, however, cosmic rays travel unimpeded. Without atmospheric or magnetic protection, any exposed environment is subject to continuous bombardment. Over time, this radiation can alter chemical structures, damage biological material, and change the composition of matter itself. Radiation zones in the universe are not limited to single sources. In many regions, multiple sources overlap, creating areas of extreme energy density. For example, the center of a galaxy may contain both a supermassive black hole and a dense population of massive stars. Together, these sources produce a complex radiation environment that affects everything within the galactic core. In such regions, the interstellar medium is highly energized. Gas is ionized, atoms are stripped of electrons, and matter exists primarily in plasma form. This plasma is constantly influenced by radiation pressure, magnetic fields, and gravitational forces, creating a highly dynamic and unstable environment. Even planets located within radiation zones face extreme conditions. Their atmospheres may be eroded by high-energy particles, and their surfaces can be exposed to lethal levels of radiation. Without strong magnetic fields or protective atmospheres, such planets would be unable to support life as we know it. Over time, radiation can strip away even thick atmospheres, leaving behind barren and exposed surfaces. One of the most intense forms of radiation in the universe is gamma radiation. Gamma rays are the highest energy form of electromagnetic radiation and are produced in some of the most violent cosmic events. Gamma ray bursts, for example, are brief but extremely powerful flashes of gamma radiation that can release more energy in seconds than the Sun will produce in its entire lifetime. These bursts are thought to originate from events such as collapsing massive stars or merging neutron stars. When directed toward a region of space, a gamma-ray burst can have devastating effects over vast distances. Even at thousands of light-years away, such an event could potentially impact planetary atmospheres and biological systems. Radiation also plays a key role in shaping the chemistry of space. In molecular clouds, radiation can break apart molecules or trigger chemical reactions that would not occur under normal conditions. This process, known as radiolysis, helps drive the formation of complex organic compounds in space. In this way, radiation is not only destructive, but also contributes to chemical evolution. In some cases, radiation can also influence the formation of stars. By compressing or heating gas clouds, radiation pressure can trigger gravitational collapse, leading to star formation. This shows that even one of the most dangerous forces in the universe can also play a constructive role in cosmic evolution. The study of radiation zones is also important for understanding the history of the universe. The cosmic microwave background, for example, is a form of low-level radiation that fills all of space. It is a remnant of the early universe, when everything was extremely hot and dense. By studying this radiation, scientists can learn about the conditions that existed shortly after the Big Bang. In more extreme environments, radiation reveals information about high-energy processes that cannot be reproduced on Earth. Observations of gamma rays, X-rays, and cosmic rays help scientists understand how black holes, neutron stars, and supernovae behave under extreme conditions. These observations are essential for building accurate models of the universe. Despite its dangers, radiation is a fundamental part of the cosmos. It carries energy across vast distances, connects different regions of space, and drives many of the processes that shape galaxies and stars. Without radiation, the universe would be far less dynamic and far less structured. Radiation zones also highlight the importance of shielding and protection in space exploration. Any future missions beyond Earth must account for radiation exposure. Spacecraft, habitats, and astronauts will need protection from high-energy particles and electromagnetic radiation. Understanding these environments is essential for safe and sustainable exploration of deep space. From a broader perspective, radiation zones represent one of the most energetic and invisible forces in the universe. Unlike heat or gravity, radiation cannot always be seen or felt directly, but its effects are profound. It shapes matter at the atomic level, influences the structure of galaxies, and affects the potential for life across the cosmos. In the grand scale of the universe, radiation is both a destroyer and a creator. It can strip away atmospheres, damage matter, and sterilize environments. But it can also drive chemical reactions, influence star formation, and carry energy across cosmic distances. It is a force that connects the smallest particles to the largest structures. As we continue to explore the extremes of the universe, radiation zones remind us that danger is not always visible. Some of the most powerful forces in the cosmos are invisible, traveling silently through space, shaping everything they encounter. In the next and final stage of our journey through cosmic extremes, we will move beyond individual sources of danger into regions where multiple extreme forces combine, creating environments so hostile that they challenge the very definition of survival itself. At the farthest edges of what we can observe, the universe becomes a place where every extreme we have explored begins to overlap. Cold regions stretch into emptiness so deep that matter barely exists. Hot regions reach temperatures so intense that atoms cannot survive intact. Gravity bends space into structures where time behaves differently. Radiation fills vast regions with invisible energy capable of destroying matter at its most fundamental level. In some places, all of these conditions exist together, forming environments so hostile that they challenge not only survival, but the very definition of what it means for a place to exist. These are the edge environments of the universe, the final boundary zones where multiple extremes converge. They are not single objects like stars or planets, but vast regions shaped by clusters of violent processes acting at once. In these areas, galaxies interact, black holes dominate, radiation floods space, and matter is stretched across enormous distances. It is here that the universe reveals its most complex and unforgiving nature. One of the most important regions where these extremes combine is the galactic center. At the heart of most galaxies lies a supermassive black hole. Around it, stars orbit at incredible speeds, gas clouds collide, and radiation is constantly produced by energetic interactions. The density of matter is extremely high compared to outer regions of the galaxy, and the gravitational field is strong enough to shape the motion of everything nearby. In these central regions, stars live in a very different environment from those in calmer parts of a galaxy. They are packed closely together, sometimes separated by distances far smaller than what we see between stars in the outer regions. This proximity leads to frequent gravitational interactions, which can alter orbits, trigger collisions, and even eject stars from the galactic core entirely. The radiation environment in galactic centers is also extreme. High-energy emissions from the central black hole combine with radiation from massive, short-lived stars. The result is a constant flood of energetic particles and electromagnetic waves filling the region. Gas clouds in these areas are often ionized, heated, and reshaped by this radiation, creating complex and turbulent structures. Despite these violent conditions, galactic centers are also sites of intense activity. Star formation can occur in dense molecular clouds, although it is often influenced or disrupted by surrounding forces. The balance between creation and destruction is constantly shifting, making these regions some of the most dynamic in the universe. Beyond galactic centers, there are even larger structures where extremes combine on a grand scale. Galaxy clusters contain hundreds or even thousands of galaxies bound together by gravity. Within these clusters, galaxies interact over billions of years, sometimes merging to form larger systems. These interactions generate enormous amounts of energy, heating intergalactic gas to extremely high temperatures. Between galaxies in a cluster lies a vast medium filled with hot, diffuse plasma. This intracluster medium is heated by shock waves from galaxy collisions and by energy released from supermassive black holes. The temperature of this gas can reach tens of millions of degrees, making it one of the hottest large-scale environments in the universe. At the same time, it is extremely thin, meaning that despite its heat, it remains almost invisible without specialized instruments. In these cluster environments, multiple extreme forces operate simultaneously. Gravity holds the cluster together, radiation shapes the behavior of matter, and high temperatures dominate the intergalactic medium. Cold voids exist between clusters, while hot plasma fills the spaces within them. This creates a patchwork of extremes across cosmic scales. Even larger than galaxy clusters are the cosmic filaments that form the structure of the universe. These filaments are massive threads of matter stretching across hundreds of millions of light years, connecting clusters and galaxies into a vast cosmic web. Along these filaments, matter flows slowly under the influence of gravity, feeding into denser regions where galaxies form and evolve. Between these filaments lie enormous voids, some of the coldest and emptiest regions in existence. Here, matter is so sparse that interactions are extremely rare. Yet even these voids are influenced by surrounding structures. Gravity from distant clusters and filaments shapes their boundaries, while faint radiation permeates their interiors. At the intersections of filaments, where matter is most concentrated, extreme conditions arise once again. Galaxies collide, black holes merge, and star formation occurs at accelerated rates. These nodes of the cosmic web are among the most active and energetic regions in the large-scale structure of the universe. In these combined extreme environments, time itself becomes a subtle but important factor. In regions of strong gravity, time passes more slowly compared to regions of weaker gravity. Near black holes, this effect becomes extreme. In hot, energetic regions, processes occur rapidly, while in cold voids, change happens over vast timescales. Across the universe, time is not uniform but influenced by local conditions. Radiation also behaves differently depending on environment. In dense regions, it interacts frequently with matter, heating, and ionizing gas. In empty regions, it travels vast distances without interference. This variation creates a complex network of energy flow across the universe, connecting distant regions through invisible channels of radiation and particles. One of the most fascinating aspects of these edge environments is how they reveal the interconnected nature of cosmic extremes. Cold regions are often shaped by lack of radiation, while hot regions are driven by intense energy output. Gravity binds everything together, while expansion of the universe stretches space on the largest scales. These forces do not exist in isolation. They interact continuously, shaping the evolution of the cosmos. In some regions, these interactions create conditions that are difficult to categorize as purely one extreme or another. For example, near active black holes in galaxy clusters, matter can be simultaneously extremely hot due to accretion processes, highly influenced by radiation from surrounding stars, and strongly affected by gravitational time distortion. These overlapping conditions create environments that are complex and constantly changing. On even larger scales, the expansion of the universe adds another layer of extreme behavior. As space itself expands, galaxies move away from each other and distant regions become increasingly isolated. Over extremely long timescales, this expansion will lead to a universe where galaxies are separated by vast distances surrounded by cold, dark space. In this future scenario, extremes of cold and emptiness will dominate most of the cosmos. However, even in this expanding universe, local extremes will continue to exist. Black holes will remain active for enormous periods of time. Neutron stars will continue to emit radiation. Galaxy clusters will persist as gravitationally bound structures. These localized regions of extreme conditions will survive even as the large-scale structure of the universe evolves. The combination of all these extremes shows that the universe is not defined by a single condition. It is defined by contrast. Cold and hot, dense and empty, calm and violent, stable and chaotic, all exist together in different proportions. The universe is a system of balances between opposing forces, constantly shifting and evolving. From a scientific perspective, studying these edge environments is essential for understanding the full range of physical laws. Conditions near black holes test gravity at its limits. Hot plasma in galaxy clusters reveals behavior of matter at extreme temperatures. Cold voids provide insight into large-scale structure formation. Radiation zones expose the highest energy processes in the cosmos. Each extreme environment contributes to a more complete picture of reality. From a broader perspective, these environments also highlight how rare stable conditions truly are. The regions capable of supporting complex structures like planets and life exist only in narrow ranges between extremes. Too much heat destroys molecular stability. Too much cold slows chemical processes. Too much radiation disrupts atomic structures. Too much gravity collapses matter. Life exists in a delicate balance between these conditions. The edge environments of the universe also remind us that destruction and creation are deeply connected. Supernovae distribute elements that form new stars and planets. Black holes shape galaxies while consuming matter. Radiation drives chemical reactions that may lead to complexity. Even emptiness plays a role in allowing structure to form over time. In the largest sense, the universe is not a collection of isolated extreme regions. It is a continuous system where all these conditions interact across scales. From the smallest particles to the largest cosmic structures, everything is connected through energy, gravity, and time. As we reach the end of this journey through the coldest, hottest, and most dangerous places in the universe, one truth becomes clear. Extremes are not exceptions in the cosmos. They are fundamental features of its structure. The universe is built on contrast, and through these contrasts, it evolves. Every region we have explored, from silent voids to blazing stars, from collapsing black holes to radiation-filled galactic cores, is part of a larger story. It is a story of transformation, where matter and energy constantly shift between states, shaping the universe into its present form. And beyond what we can currently observe, there may be even more extreme environments waiting to be discovered. The universe is vast, and our understanding of it is still limited. Each new observation reveals new layers of complexity, new boundaries of temperature, gravity, and energy that push our understanding further. In the end, the universe is not defined by comfort or stability. It is defined by extremes, and in those extremes we find the true nature of reality itself.